In this video, we will explore how DC motors work. We will start with the basics of magnetism and electromagnetism and see how these concepts come together in a DC motor to convert electrical energy into mechanical energy. We will take a look inside an industrial DC motor, which consists of hundreds of precisely engineered components, and explore each one in detail. Magnets and magnetic fields lie at the core of every type of electric motor. The interaction between magnetic fields is the fundamental principle behind how all electric motors operate. That's why understanding magnets and magnetic fields is crucial to grasp the working of any electric motor. Magnetic fields can be visualized as lines of magnetic flux surrounding a magnetic object. To keep things simple and easy to understand, I'm showing only a 2D cross-section of the magnetic field. Outside the magnet, the field lines go from the North Pole to the South Pole. Inside the magnet, the direction is from south to north, because magnetic field lines always form closed loops. One of the most fundamental properties of magnets is that like poles repel each other, while opposite poles attract. This behavior is a result of the interaction between their magnetic fields. The magnet you're seeing here is a natural bar magnet, made of magnetite, a naturally occurring form of iron oxide. At the microscopic level, magnetite contains millions of magnetic domains, each acting like a tiny magnet. In a magnetized bar, these domains are aligned in the same direction, which gives the material its overall magnetic properties. One major limitation of natural magnets is that we cannot control the strength or direction of their magnetic field. This lack of control makes them unsuitable for applications where precise and consistent magnetic behavior is required. These limitations can be easily overcome by using electromagnets instead of natural magnets. Electromagnets operate on the principle of the magnetic effect of electric current. When current flows through a conductor, it generates a magnetic field around it. The direction of this magnetic field can be determined using the right-hand thumb rule. If you point the thumb of your right hand in the direction of the current, your curled fingers show the direction of the magnetic field. If we take this straight wire and wrap it into a coil commonly known as a solenoid, the magnetic field becomes much stronger. This is because the magnetic fields generated by individual turns of the wire combine constructively. One of the biggest advantages of an electromagnet is that we can control both the strength and direction of its magnetic field. The strength can be increased either by increasing the number of turns in the solenoid or by increasing the current passing through it. Likewise, the direction of the magnetic field can be reversed simply by reversing the direction of the current. When a ferromagnetic material is placed in a magnetic field, most of the magnetic field lines are concentrated through the material. Ferromagnetic materials are those that are strongly attracted to magnets, with iron being the most well-known example. These materials contain magnetic domains, tiny regions where the magnetic moments of atoms are aligned. Under normal conditions, these domains are oriented randomly, so the material exhibits no net magnetic field. However, when exposed to an external magnetic field, the domains begin to align in the direction of the field. This alignment significantly enhances the magnetic flux through the material. In this way, ferromagnetic materials act like conductors for magnetic fields, offering a path of low magnetic reluctance, much like electrical conductors provide a low resistance path for current flow. One of the biggest advantages of working with magnetic fields is that their path can be reshaped and guided using ferromagnetic materials. This is why all types of electric motors and even generators rely on ferromagnetic materials to direct the magnetic field lines in a controlled and desirable manner. Now that we've covered the fundamentals of magnetism and electromagnetism, let's take a closer look at the operation of the DC motor. This machine consists of two main components: the cooling blower, which ensures proper heat dissipation during operation, and the motor itself. Before we dive into the details of each component, let's first take a basic overview of the motor's mechanical design to understand how everything is structured and connected. The motor mainly consists of two primary parts: a stationary part called the stator, and a moving part known as the rotor or armature. These are enclosed within a heavy-duty outer frame that holds everything together. This frame is a robust structural element designed to support the massive weight of the motor and blower, as well as withstand the mechanical forces generated during operation. It also plays a crucial role in securing the motor firmly to its foundation. At both ends of the motor, you'll find components called end bells or end covers. These are mounted to the outer frame and serve multiple purposes. They support the motor's bearings, help align the rotor with the stator, and enclose the internal components to protect them from dust and external damage. In large industrial motors, end bells are built strong enough to handle both mechanical loads and thermal expansion. The rotor is supported by bearings housed within the end bells. Spherical roller bearings are commonly used in industrial DC motors, as they are capable of handling both radial and axial loads. The rollers inside these bearings are slightly convex in shape, which increases the contact surface area and allows the bearing to tolerate slight misalignments during operation. This design improves durability and reduces localized stress, making double roller bearings ideal for large industrial motors that operate under heavy mechanical and thermal conditions. The terminal box is an external enclosure mounted on the motor's frame, typically on top or to the side. It houses the electrical connections between the motor windings and the external power supply. The terminal box houses heavy-duty bus bars that deliver power to the armature. In large industrial motors, operating currents can be very high depending on the voltage and power rating, so multiple parallel cables are used to divide the current and minimize electrical losses and heat generation. A special insulating piece, usually made of durable plastic, is used to safely pass the conductor bars through the main frame into the interior of the motor. This prevents any risk of short-circuiting between the conductor bars and the motor frame. The terminal box provides a safe and organized space for cable termination, while also protecting the electrical connections from dust and moisture. Sight windows are provided on both sides of the main frame, allowing operators to visually inspect the condition of the commutator, brushes, and other internal components. Now let's focus on the stator, the stationary part of the motor, whose primary purpose is to create a constant magnetic field. The stator mainly consists of a yoke and a set of stator poles, which are securely fixed to the yoke using bolts. The yoke is constructed as a solid piece using a high permeability magnetic material, such as cast or rolled steel. The yoke plays a crucial role in completing the stator's magnetic circuit, while also serving as a structural backbone that holds the stator poles firmly in place and withstands mechanical stresses during operation. Each stator pole is composed of two parts: the pole body and the pole shoe. The pole body is the central section that carries the field winding, while the pole shoe is a wider section at the end that spreads the magnetic flux over a larger area of the armature. This helps create a more uniform magnetic field and reduces localized magnetic saturation. A distance piece is placed between the pole body and the yoke to finely adjust the air gap between the stator and the armature, which is critical for efficient operation. Rather than being made from solid steel, The stator poles are constructed from a stack of insulated laminations made of silicon steel, with each sheet around 0.5 millimeters thick. This laminated structure minimizes eddy current losses and improves the motor's overall efficiency. On both sides of the laminated stack, thick steel plates are added for mechanical stability, and the entire assembly is clamped tightly using rivets to hold everything in place. In modern machines, the pole body and pole shoe are manufactured as a single laminated unit. In contrast, older machines often featured a design where the yoke and pole body were cast together as a single piece, and a laminated pole shoe was attached separately. Coils are wound around each stator pole to generate the magnetic field essential for motor operation. To support the winding both mechanically and electrically, an insulated structure is used. This structure holds the coil in place, maintains its shape, and helps absorb mechanical stresses during operation. The coils are made using copper conductors or strips, insulated with a varnish coating to prevent short circuits between turns. The number of turns, the thickness of the conductors, and the voltage range of the field winding are all carefully selected based on the motor's size, magnetic requirements, and intended application. These factors directly influence the strength of the magnetic field produced by each pole. For proper insulation and long-term durability, the windings are tightly wrapped in layers of fiberglass or cotton tape and then impregnated with varnish or resin. This process protects the coils from moisture, vibration, and electrical breakdown, while also enhancing their mechanical strength. The number of stator poles is a crucial design parameter in any DC machine. It directly influences other key components, such as the armature windings, commutator segments, and the number of brushes required. The stator poles are connected in series and arranged in such a way that their magnetic polarity alternates. This alternating polarity is crucial for maintaining a continuous interaction with the rotating armature. Series connection ensures that the same amount of current flows through each pole, resulting in a balanced and uniform magnetic field throughout the motor. Between the main poles, small auxiliary poles known as interpoles are fixed. These are mounted on the yoke using bolts, just like the main stator poles. Depending on the design, interpoles may be constructed from laminated sheets or as solid pieces. Their primary function is to improve commutation by counteracting the effects of armature reaction. Interpoles are also wound with conductors, but unlike the main field windings, they use thick conductor bars with very few turns, as they carry the full armature current. Another important feature in higher power DC motors is the inclusion of compensating windings. These windings are embedded in axial slots cut into the pole shoes and are typically arranged in a concentric coil pattern. Like interpole windings, they are made using thick conductors, as they also carry the full armature current. Interpoles and compensating windings are connected in series with the armature to ensure their magnetic effect varies proportionally with load. We will explore their role and design in greater detail when we discuss armature reaction and magnetic field distortion. Now let's begin our discussion on the rotor of a DC motor. Earlier in the video, we discussed how the interaction of magnetic fields is the fundamental principle behind the operation of all electric motors. The stator produces a magnetic field through its pole windings. Similarly, the rotor, also known as the armature, has its own windings, called armature windings. When current flows through these windings, the rotor generates its own magnetic field. This magnetic field interacts with the stationary field of the stator, and this interaction produces the torque that drives the rotor into rotation. The rotor consists of four main components: the shaft, core, rotor windings, and commutator. The shaft plays a crucial role in transmitting torque from the motor to the driven machine. A coupling key is used to securely connect the motor shaft to external mechanical systems. The shaft is typically made from forged steel, selected for its high mechanical strength and excellent notch impact resistance. It is designed to withstand torque levels up to 10 times the rated value, ensuring reliable performance even during rare cases of severe overload. The rotor, or armature core, is one of the most critical components of a DC motor. It provides a low-reluctance path for the stator magnetic field to interact with the armature coils. It is constructed from a stack of thin, insulated laminations typically around 0.5 to 0.7 millimeters thick, made of high permeability magnetic material. These laminations are individually coated with varnish or another insulating material to minimize eddy current losses. By stacking them together, a core section is formed. Complete armature core is consisting of multiple such sections, with each section separated by ventilation ducts. These ventilation ducts are formed by spot welding vent spacers to the end laminations of each core section. They play a crucial role in allowing air to circulate through the rotor, helping to maintain safe operating temperatures during continuous or heavy-duty operation. The entire assembly of core sections is securely clamped using clamping discs and long bolts, ensuring mechanical stability under high rotational and magnetic forces. The U-shaped sections around the outer circumference of the core are known as armature slots. Armature windings are carefully placed within these slots, enabling them to interact directly with the stator's magnetic field and generate torque. Based on how the coils are connected and arranged, DC motors primarily use two types of windings: lap winding and wave winding. The core concept behind both types is quite similar. In this video, I will focus only on lap winding, which is commonly used in high-power DC motors. Armature coils are made using thick conductors and have significantly fewer turns compared to the field windings, since they carry much higher current. Each armature coil consists of two main parts: the coil sides, also called conductor bundles, which lie within the slots, and the overhangs, which are the portions of the coil that extend outside the slots. The overhangs of the armature coils are mechanically supported by structures welded to the clamping disc, ensuring they remain secure during operation. Each armature coil is shaped precisely using coil pullers, allowing it to fit perfectly within the armature slots. One crucial design parameter is the distance between the two coil sides of a single coil, which is calculated based on the number of armature slots. This distance is known as the coil pitch. Coil pitch is defined as the number of armature slots between the two sides of the same coil. Pole pitch, on the other hand, refers to the number of armature slots per pole and represents the distance between the centers of two adjacent stator poles. For this machine, there are 8 stator poles and 120 armature slots. Therefore, the number of armature slots per pole is 15. When current flows through an armature coil, the direction of current in the two coil sides is opposite. Therefore, we aim to position these two sides under stator poles of opposite polarity. This ensures that the torque produced by both sides adds up in the same direction. Each coil side acts as a current-carrying conductor placed in the magnetic field of the stator. Due to the interaction between the magnetic field of the stator and the magnetic field produced by the coil, a force is exerted on the conductor. One important point to note is that only the coil sides positioned within the armature slots directly under the stator poles contribute to torque production. The overhang portions of the coil lie outside the magnetic field, and therefore do not play a role in generating motor torque. The direction of this force, and hence the resulting torque, is determined using Fleming's left-hand rule. Fleming's left-hand rule is used to determine the direction of the force acting on a current-carrying conductor placed in a magnetic field. In the case of a DC motor, the armature coil sides act as the conductors, while the magnetic field produced by the stator serves as the external field. According to Fleming's left-hand rule, if you stretch the thumb, forefinger, and middle finger of your left hand at right angles to each other, pointing the forefinger in the direction of the external magnetic field, and the middle finger in the direction of current in the conductor, then the thumb will indicate the direction of the force acting on the conductor. Although the two sides of the coil carry current in opposite directions, they are also placed under stator poles of opposite polarity. As a result, the magnetic field direction is reversed for each side, and the forces on both coil sides act in the same rotational direction, causing the rotor to turn in one direction. Armature coils often use multiple insulated strands instead of a single thick conductor. This approach helps minimize eddy current losses as the conductors move through the stator's magnetic field. Each strand is coated with varnish for insulation, and all strands are connected at both ends to function as a single electrical path. To insulate the windings from the rotor core, slot liners are inserted into each rotor slot before placing the conductors. In a typical DC motor, one side of each coil lies in the lower half of a rotor slot, while the other side is placed in the upper half of a different slot. The arrangement of many such coils forms the complete rotor winding. Each rotor slot carries two coil sides belonging to two different coils. This configuration is known as a double-layer winding. This design helps reduce the total number of rotor slots required, allowing for a more compact rotor diameter. After placing the conductors, slot wedges typically made of fiberglass are inserted to close the rotor slots. These wedges secure the conductors firmly in place and protect them from the centrifugal forces acting on them during rotation. The winding arrangement used here is a simplex lap winding. In this type of winding, each coil provides a single path for current to flow. Simplex lap windings are widely used in DC motors of small to medium power ratings due to their simplicity and ease of construction. However, in large industrial motors where current ratings are much higher, a duplex or even multiplex winding configuration is used instead. These advanced configurations are geometrically similar to simplex windings, but each coil consists of multiple insulated strands. Each pair of strands forms an independent path for current flow, significantly enhancing the motor's current carrying capacity by dividing the total current into multiple parallel paths. One of the key advantages of multiplex windings is their ability to improve the commutation performance of a DC motor. Electrical power is supplied to the rotor windings through the commutator and brushes, which maintain continuous electrical contact with the rotating coils and ensure smooth operation of the motor. Since the rotor is a rotating part, electrical power cannot be supplied directly through fixed connections. To energize the rotor windings, a specialized component called the commutator is used. The commutator is made up of multiple thin copper sections, known as commutator segments. Commutator segments are typically made from high conductivity, hard-drawn copper to withstand the high current demands and the mechanical friction generated by the brushes during operation. Commutator segments are tightly clamped between two end discs, called V-rings. These segments are electrically insulated from each other and from the V-rings using high-quality insulating materials. such as mica sheets. The total number of commutator segments depends on the number of armature slots and the type of winding used. For a simplex lap winding, the number of commutator segments is equal to the number of rotor slots. In a triplex winding, where each coil has 3 electrically independent paths, the number of commutator segments becomes 3 times the number of rotor slots, since each conductor strand requires its own dedicated segment for independent energization and de-energization. Because the commutator has a much smaller diameter than the armature, risers, which are conductive strips, are used to connect the commutator segments to the coil ends. Risers are connected to both the commutator segments and the ends of the armature coils using soldering or brazing, ensuring a secure and conductive joint. Spacers made of insulating material are inserted between the risers to keep them electrically isolated from each other and prevent short circuits between adjacent connections. Electrical energy from the external power source is supplied to the commutator using carbon or graphite brushes. The position and performance of these brushes are critical to the proper functioning of a DC motor. The exact specification and material of the brushes depend on several factors, including motor speed, operating voltage, and the physical dimensions of the commutator segments. Most industrial DC motors use brushes made of graphite-based materials, which offers good conductivity and wear resistance. Brushes are held in place by brush holders, which maintain their position against the rotating commutator. A combination of a phosphor bronze spring and a pressure finger is used to apply consistent pressure on the brush, ensuring firm and reliable contact with the commutator surface. Brushes are mounted on brush arms, and multiple brushes can be installed on a single arm. To establish a flexible electrical connection between the brush and brush arm, twisted copper flexible conductors are embedded into the brush during manufacturing. This not only increases the total contact area, but also helps distribute the current, reducing wear and heat generation. In lap winding configurations, the number of brush arms is typically equal to the number of stator poles. 2 bus bars supply electrical power to the brush arms. These brush arms are connected to the bus bars in such a way that their electrical polarity alternates, just like the alternating magnetic polarity of the stator poles. Electrical energy flows from the bus bars to the brush arms, then to the brushes, into the commutator segments, and finally reaches the armature coils via the risers. The entire brush assembly is mounted on a support disc, which serves as a stable mechanical base for the brush arms. Each brush arm is attached to this disc using insulated bolts and pads to ensure electrical isolation from the disc. The support disc itself is rigidly bolted to the main frame, firmly securing the entire brush assembly in place.